second talk in this session is going to be by uh, uh, Raghu Krishnamurthy. He is software engineer at Facebook. He works on mostly on quantization and PyTorch group. Before that, he worked at Qualcomm for 15 years, and he has MS degree from UIUC. So Raghu, it's very exciting to have you back again, and some of the recent of your quantization work. So we're really looking forward to your talk. So it's all yours.
Thanks, Raj, for the intro. I just want to make sure that everyone can see my screen.
Yes, we can see. Try to in full mode. I think we can see. We are good.
Okay, sounds good. So I think probably most of you have listened to Tijman's excellent talk earlier today. So you can think of this talk as sort of a complement to that talk, where you're sort of looking at quantization sort of in a more applied way. And we'll get started right away. So why quantization? Again, I'll be brief because I think most of you have probably seen this. So there's an explosion sort of in the amount of compute on resource constrained devices where we need AI. And why do we need machine learning? There are many reasons. In fact, one segue from I think the previous talk on privacy is that on-device inference, one of the big reasons now I think there's a lot of interest is that it's sort of step zero towards getting privacy, in the sense that if at least your data is sort of on your device, you're doing the inference on your device, at least that data doesn't need to go to the cloud. And of course, there's much more. Second thing is that this is not a problem just at the edge. This is also a problem more broadly for the entire AI sort of community. So if you look at vision models, you see that if you want to get to state-of-the-art performance, you actually have to pay a cost in terms of complexity. And if anything, this is true even more so in the domain of NLP. So if you look at, for example, all the excitement around GPT-3, that sort of caught my eye in that paper is that you see that there is no saturation yet. As in, if you throw more parameters at it, if you throw more cycles at the problem during training, your validation loss just seems to go down. So all of this also causes an issue for data centers. And you may have sort of different motivations for sort of between the server and the edge. And the edge, you're more concerned with latency, you're concerned with just making sure that it fits inside like the resource budget that you have. On the server side, latency and power is increasingly important. And this is where quantization really helps, amongst many other advantages. And there's just a slide showing sort of the gains that you can get. And I just want to sort of zoom out a bit now and say that, what are all the things that are happening right now to sort of solve this problem. And if you look at sort of the end-to-end flow on how models are built, there's usually a manual process in the very beginning where there is iteration over architectures. Do I use attention models? Do I use residual connections? What's my data set? How do I augment my data? What's my loss function? So there's sort of manual iteration there. And once that is done, sort of an architecture is picked. And then there's hyperparameter tuning. This could be, of course, training hyperparameters like the learning rate, or you in addition, more often you're sort of tweaking your model. You're changing like the number of feature maps, your kernel sizes, number of layers. And around this point, when your architecture is sort of stabilizing, is when usually compression sort of enters the picture, and then you try to apply quantization and sparsity. And typically, quantization can be done with or without training. In most cases, in fact, it's done post-training. But in general, quantization and sparsity, again, require training and eval loops. And once all of this is done, these models have to be deployed in some hardware platform. And this is where compilation comes in. And finally, this all has to map to efficient kernels. And if you sort of try to sort of throw a number at what can you gain at each of these steps, the first part of the pipeline where you sort of pick the architecture is where you can get a lot of gains. Obviously, picking a mobile net over a REST can give you like 100x gain. Hyperparameter tuning can again give you like a few orders of, can give you a 1 to 5x sort of gain. Again, this is a rough rule of thumb. With quantization and sparsity, with quantization, sort of the upper bound on your gain, it's about 4x in practice. Again, I'm just comparing floating point FP32 to int8. Obviously, the number will depend on the patient that you pick and if you have special hardware acceleration. With sparsity, the number again depends on what sort of sparsity we are talking about, what level of sparsity are we achieving in the network. But again, as a coarse rule of thumb, I would say that up to 4x, more often something close to 2x is what you see when you sort of try it out on some models. And then at the bottom of sort of the flow, the kernels, you can get a huge improvement. If you sort of fuse operations, or you just sort of change your loop ordering, or you use the right SIMD construct, or you optimize for shape, you can get a big 10x improvement. In this talk, I'm going to primarily focus on sort of the third block, which is quantization sparsity, but I'll refer to sort of the boxes above and below briefly. So a quick summary on sort of where quantization is in practice from the lens of PyTorch is in like the next few slides. So quantization has a bunch of advantages. Again, I think you saw a lot of this in the preceding slides, so the preceding talk. So I'm just going to be brief here. So I just want to spend a couple of minutes on how we see quantization being used in practice by both internal users at Facebook and by the open source community. So there are sort of three paradigms in which people use quantization. The first step is where quantization is sort of hidden with the kernels. So in this case, for users, it's agnostic. It's almost like a one-line call. And this sort of transforms their model and they get a speed up. We refer to this flow shown on the left as dynamic quantization. And we call it dynamic because in this case, your activations get quantized on the fly. Your compute happens with lower precision arithmetic and your activations get dequantized. So it's completely transparent outside of the kernels. Of course, your weights are quantized, but that doesn't require any data. So this scheme is sort of fully data free, doesn't require any calibration. And it works surprisingly well in practice. The reason is that if you're limited by compute or you're limited by memory bandwidth for your weights, this scheme sort of checks off both of those boxes. The only catch with this scheme is that it does require floating point support because you're going back between FP32 and int8. And in addition, your activations are in floating point. So in cases where that's important, and that covers, if you want to sort of get your model running on resource constrained devices, or your device doesn't support floating point that well, or memory bandwidth of activations is important, then you would do static quantization. And we see this widely used, particularly for mobile deployments. And in this case, the simplest flow is where you train the model, and literally after that, you just do a simple calibration to figure out the dynamic ranges for your activations. And then you, of course, need quantized kernels to run this compute on. The third flow is when you have use cases that are sensitive to quantization. And this can occur for a variety of reasons. It can occur either if the architecture that you're picking is sensitive to quantization, or if the application domain that you're picking is sensitive to quantization. An example is classification is a lot easier conceptually than, say, denoising or super resolution. So regression problems are much harder than classification problems. And those are cases where you would want to model quantization during training so that your network can sort of compensate for it. And then at the end of it, you have to sort of take your train model, which has floating point operations on a GPU, and map it to quantized kernels. So just a quick word on terminology. So when we're talking about post-training quantization, usually we're talking about int8. And in practice, we quantize tensors to different granularities. You can either quantize the entire tensor in a network, or you can quantize a tensor along a particular dimension. And the most common dimension that we use is either rows, if you're thinking of matrices, or channels, if you're thinking of, say, kernels. And we refer to this as per row or per channel quantization. advantage of doing quantization of the finer granularity is that you introduce lesser numerical error. And the added benefit is that this can be done with very little overhead on your kernels. In fact, in practice, there is no overhead in kernel implementations between, say, per tensor and per channel quantization on CPUs. So this is sort of very widely used in practice. And then just to sort of for completeness, when we talk about quantization about training, what we do is we insert fake quantization as an operation during training. And what this does is it mimics quantization, but with floating point arithmetic. The reason being that training is done on GPUs, and we need to optimize the arithmetic on GPUs. And on the backward pass, we just let the gradients go through, we just clip them. Okay, so where are we in terms of numerics with and speed up with quantization? So here are some results that we saw on some standard models with different schemes in PyTorch. So on ResNet 50, sort of a workhorse for computer vision, just simple post-training quantization gives you close to floating point. We see just a 0.2% accuracy drop with a 2x speedup. This was on an Intel Skylake. And for NLP model, in fact, we just tried quantization. Of course, we did per channel quantization of the weights. In this case, at least on the MRPC benchmark, on the MRPC score for Glue, we saw that there was pretty much no measurable drop in the F1 score. The story is a bit different when you look at smaller models. And here is sort of using MobileNet V2 as a proxy. You see that for some of these smaller models, just doing post-training quantization didn't work. The accuracy drop was too high. Even sort of trying it with per channel quantization didn't really close the gap. And you needed smaller models. And here is sort of using MobileNet V2 as a proxy. You see that for some of these smaller models, just doing post-training quantization didn't work. The accuracy drop was too high. Even sort of trying it with per channel quantization didn't really close the gap. And you needed quantization-aware training to sort of close the gap. And once you do that, in fact, you can even fall back to quantizing at a coarser granularity. Even per tensor quantization works. And as you see, we see speedups some anywhere between like 1.5 to 2x to 4x. Of course, the speed comparison comes with many caveats. It really depends on the efficiency of the floating point implementation that you're comparing with. But 2x is sort of a good number to sort of shoot for in practice. Sparsity, now moving on to sparsity. Sparsity is in a much, I would say compared to quantization, it's in a much early. And I just wanted to define a bit of terminology here before I get into the details of the slide. So when I mean sparsity here, I'm talking about not removing rows and columns of matrices. This is structured sparsity where you're removing where groups of consecutive values are zeros only in the weights. So specifically, if you think of your weight as an m by n matrix, you could be zeroing out consecutive, say, 4 elements or 8 elements or 2 by 4 elements in this matrix. And the idea here is that your weights are known ahead of time. And if your weights have a structured pattern of zeros, you could implement a kernel that takes advantage of the part of the zeros in your weights and therefore do lesser multiplies. Of course, this is not free because now your memory accesses are not regular. So you will not be able to sort of see the theoretical speedup that you would expect. And another thing to clarify is that we are not exploiting the sparsity in the activations because that's dynamic. Though a lot of the activations are zeros when you have non-linearities like the ReLU, that's not something that we can exploit. So if you look at sort of a similar chart for what sort of gains can you get with sparsity, it's a bit nuanced because it really depends on what sort of sparsity levels that you can get. So assuming that you can get to like 75% sparsity, by that I mean 3 out of 4 terms of your weights are 0 and it follows some kind of structure, you could get to about a 2x speedup in the compute. But the caveat again with sparsity is that it's not at the level of maturity as quantization in the sense that you don't see yet libraries sort of having good support for sparse say, gem operations or sparse convolution operations. And sparsity in practice, you would sort of do sparsity usually on models that you're also interested in quantizing because they sort of look at the same domain. And one interesting thing that we see with sparsity is that almost always sparsity goes with training. Doing sparsity post-training just doesn't meet the accuracy versus speedups that people would want in practice. So you can sort of combine sparsity either with post-training quantization, as shown in the left, or you can combine sparsity with quantization aware training. And in that case, essentially you model the sparsification of your weights. You sort of apply a mask to sparsify your weights. And then you have a fake quantization operation at training. And once the model is trained, you convert it, you map it into kernels that are both that work with both quantized and sparsified weights. So we don't have, at this point, there is not much of support for sparsity in PyTorch, though there's a lot of active work in progress. So I just want to point out to sort of results out there in the literature to sort of motivate the gains. So here are a couple of results, one from TVM and the other from Google on mobile. And both of them show that we can get of an order of a 2x sparsity, 2x speed up, provided you have high enough sparsity. Okay, so just wanted to sort of spend the rest of my talk sort of talking about the current challenge status of quantization, what the challenges are, and sort of what would be where things could be, say, a year or two down the road. So quantization at this point is widely used. As I said before, we use it at Facebook. We see the community using it for across devices, primarily, of course, I'm talking about x86 and ARM CPUs. It is used across domains. So that's one of the advantages of quantization. It seems to work very well across use cases, recommendation models, vision, and so on. In terms of precision, I would say that the industry is still broadly at 8 bits, and it's primarily because first reason is that 8 bits seems to be a sweet spot in the sense that you don't have to work too hard in many cases to get to reasonable accuracy trade-off. Second thing is that there is not much of hardware or kernel support. So it's a bit of a chicken and egg problem. I think as sort of more hardware support occurs, this could change. But even though, quantization does work, in practice, it's been quite challenging. And I want to sort of point out some of the challenges and sort of the mitigations that we have taken in PyTorch. The first thing is that quantization ideally should be like a compiler flag, right? You sort of turn this flag on, you go from debug to optimize, and you sort of get a speed, and it's easy, right? But in practice, it's much harder because if you think of quantization as integrating with software, which is what models are, you write your model in Python, write it in PyTorch, and once you want to quantize it, you have to sort of go and change your source code at multiple locations, and then you try quantization. And this has been sort of hard if you want to do it in scale. And the thing that we've been working on in PyTorch is to integrate quantization closer with. Essentially, we build an intermediate representation of the entire user code of the entire machine learning model. And then we can automate the entire process of quantization. So it's currently there as a nightly feature in PyTorch. It's not yet sort of a feature with the API stable, but I have a link in case folks are interested in sort of taking a look at what this looks like. Second thing is that to get the actual performance wins with quantization, I think there is a lot of work that needs to be constantly done at the bottom part of the stack. By that, what I mean is that processes continue to evolve, SIMD capabilities evolve, models change, and there has to be like a constant investment on the kernel side to make sure that you sort of get the best speed up exploiting SIMD, and also making sure that for all the shapes you get the right speed up. And what this has meant in practice is that, and there has to be like a constant investment on the kernel side to make sure that you sort of get the best speed up exploiting SIMD, and also making sure that for all the shapes you get the right speed up. And what this has meant in practice is that you need experts to sort of hand optimize the kernels. And this is, and you also need to make sure that the framework does not cause any overhead. For example, with quantization, depending on your underlying kernels, you may need to sort of have your activations at a particular layout. And you don't want to sort of pay the penalty of sort of reordering contents in memory. And your framework needs to be mindful of this. And in PyTorch, we have optimized for this. And sort of the same comments hold to an extent for quantization-aware training too, because quantization-aware training is going to consume more GPU resources. So efficient operator implementations, fusion, the same sort of work also needs to be done to make sure that the overheads are kept in check. The other big challenge with quantization is that hardware support is quite complicated. Again, taking analogy with compilation, it's not as simple as sort of using a different compiler or just targeting your source code to a different processor. Since quantization changes numerics and the capability of the numerics itself changes for every backend, the story is much more nuanced. So for example, depending on the hardware you pick, you may find that only certain operators support quantization. You may also find that the fusion is different. You may also find that the numerics of quantization itself is different. And the way I think we tried to sort of address this challenge, albeit in sort of an incomplete way as of now, is to allow for a lot of customization. The idea is that PyTorch quantization, there is sort of a reference workflow for users who are not experts who just want to get something done. And for advanced users, every step of the pipeline is customizable. In fact, with the customization and with sort of integration with compilers like Glow, there is sort of a path for, say, a new backend to be able to take a PyTorch model, use the quantization stack, and then use Glow to sort of lower the model into the hardware of interest. Another dimension, sort of looking from the user point of view, is that debugging quantized models is hard, since that this is a transformation of your model. So in some sense, your source code has changed, and there is no easy way to sort of localize it. Let's say you quantize a model, you find the accuracy is not good. It's sort of hard. So right now, early stage, what most users do is sort of iterate, sort of edit their code and find out what's going on. But what we've been sort of building is a numeric debugger. And the idea is sort of analogous to regular debuggers. The idea is that it'll localize and say that, hey, maybe this part of your model is what is causing the quantization error. And the last challenge is that the state of the art is constantly changing. As you sort of saw in Tijman's talk earlier today, there are a lot of innovative techniques that are coming up. And so there are always many questions with respect to quantization. When we see users sort of having questions on which technique to pick, or I kind of want to go to very low precision, or my application is very sensitive to quantization. So for a lot of these, usually I would say that if you have support for 8 bits, a good starting point is just doing simple post-training quantization. If that doesn't work, quantization-aware training is usually good enough if you have 8 bits. If you sort of want to push the envelope and sort of go to lower precisions, learnable fake quantization with quantization-aware training, where you sort of directly learn the scale and 0 point via backpropagation, is a promising technique. Techniques like equalization that was developed by Tijman and his team, again, are also very promising. So we have some support for these things. We have support for modeling lower precision with fake quantization in PyTorch. We also have support for directly learning the scale and 0 point via backpropagation. And there's also some simple support for equalization. So that's sort of where the current where quantization is currently, and our current attempt at making it easier and sort of helping to make it scale for more models. Now I want to spend a few minutes sort of looking ahead at where, sort of trying to predict where things will be, say, a year or two down the road. So starting with the bottom of the stack, I think there are going to be significant improvements to kernels. And this is primarily because of better investments in compiler and runtime technologies. So across the industry, you sort of see techniques like PVM, GLOW, JAX, all allowing for generation of better kernels. And this becomes very important if you want to sort of optimize your kernel for the right shape. The second interesting thing that's happening is that new hardware is coming up. And what we see with new hardware is that the advantage of quantization over floating point is just much higher. I think in CPUs, as I mentioned earlier, we see like a 2x improvement. But what we see now is that you could see anywhere from 8x to a 16x improvement by using quantization. And that's primarily because you can squeeze in a lot more math for the same sort of area as a floating point unit if you use lower precision. So what you end up seeing is that if you use 8 bits, say 8x speedup, if you can go down to lower precision, particularly in the newer accelerators, you could get to even higher performance. So there is going to be the importance of just plain quantization in terms of the speed up is going to become even higher. And we're also seeing that the newer hardware that is, I expect to see more improvements in terms of support for sparsity. The other part where there are going to be significant improvements, sort of again looking ahead, is in sort of integrating the quantization sparsity tuning with sort of the model hyperparameter tuning and architecture definition itself. So one thing that that should happen, say down the road, is fully automatic quantization and automatic sparsification, because your model has many layers, many tensors. Some of them are going to be sensitive to quantization. Some of them are going to be very sensitive to sparsify. And having full automation that sort of takes care of all of this and sort of optimizes what can be optimized and keeps what cannot be optimized while meeting an accuracy budget would make it really simple for users. And eventually, quantization and sparsity you can view those as modifications, simple modifications sort of to a model architecture. You're changing the weights in both of these cases. Down the road, I expect these techniques to sort of merge with model architecture tuning itself. So eventually, I think sort of the holy grail is that you have a base model architecture, and then you have sort of an automated tool that lets you tune the number of feature maps, the kernel size, the number of layers, along with the sparsity level that you would pick for these models. There are many interesting papers in this area. Just wanted to sort of point to a couple of papers for folks who are interested. So to conclude, quantization and sparsity, quantization in particular is being widely adopted now, and there are challenges, but I think there is. I would say that the benefits of quantization are only sort of, we are still in the early days of seeing the benefits due to quantization in practice, and with improvements sort of coming down the track, pretty confident that as we look at this, say, a couple of years down the road, we're going to see much higher benefits. And this is going to be crucial to sort of handle the explosion in model complexity and the explosion in terms of needs for resource constrained compute in the future. I'll end my talk by just pointing to resources that are there. If we encourage people, we have a very active community working on PyTorch in general, and we welcome GitHub contributions. We also have an active forum for quantization-related topics in PyTorch. Here are some resources and pointers to documentations for folks who would be interested. With that, I'll end my talk, and I'm ready to take questions. Hello?
Hi, can you hear me? I was hoping to ask a question.
Sure. Is this Kushal? Yes, I can hear you.
This is Stone right now. Hi.
Oh, hi.
Hi. Yeah, I was just curious. It looks like, so in the roadmap you have all these quantization tool chains coming up, and is there ever any plans to build up like a TF Lite similar kind of framework where they have their own like graph format that they use for the edge inference and stuff like that?
So we already have PyTorch mobile. So
okay.
one conscientization I think that's been made in PyTorch is sort of not to let the code base fragment. That was one of the challenges that TF Lite faced. So
Right.
you will sort of still be able to use the same sort of JIT serialization, and then there would be just additional optimizations that are done for mobile.
Okay, so we won't have to worry about like a completely different graph format like we do with TF Lite right now, and it's not exactly
Yes.
like once you've converted to TF Lite, it's a lot harder to get it back to TensorFlow.
Yes, and I think we are working on avoiding that with PyTorch. So just JIT.save, JIT serialization should work for mobile also.
Oh, cool. Yeah, thanks.
Thank you. I guess my microphone was mute. I will continue
Sorry,
sharing the
please.
session. I think there is one more question. Kushal?
Hey, really good talk, Raghu.
Hey, you're muted, I think, Kushal. I can't hear
Yeah,
you.
yeah, Kushal, it seems that
Oh,
you're
I'm so
muted.
sorry. Can you hear me now?
Yes,
Yes.
we can hear.
Okay. So I find this two asks a little bit conflicting because in one way we are saying that we need better debuggability across layers because there are so many dimensions where we can apply quantization. On the other hand, we are saying that everything should be hidden under a compiler and end to end where the things should happen out of the the way of the developer, because at the end of the day we just want to use the model. We don't want to worry about what's going on. Traditionally compilers don't do that, right? Compilers they map to lower level instructions, but they don't touch the data type. Here we are saying that we can touch the data type as well. That's where the contradiction in my mind, or the conflict. So what do you yeah, I just wanted to know your thoughts on it.
I think it's a great point. I think quantization is compilation, but it's lossy compilation, right? It's sort of the kind of compilation that wouldn't be accepted in practice. So I would say that there is a tension between where we are now and where we'll be in the future. I think for now you need better debugging tools and so on. But imagine that down the road you sort of have a technique that allows you to sort of automatically trade off and say, if you quantize this part of the model, you get this speed up or this accuracy. Once you have something like that, then sort of there will be lesser need for the debug tools because the tool chain has just matured. And the user just sort of turns a crank, sees a bunch of choices, and picks the one that works for their use case.
But is there a good notion of what a mathematical good numerical tool would do? I mean, for example, scale divergence is something that I see used very often, but none of the tools actually, at least visually, show anything that, right? So we have to develop it, integrate such a method into our into the quantization and then see what the benefit it gives, right? So it's still very analytical, very manual.
Yes, so that's why I think that's a good point. So with quantization, I don't think there's going to be a closed form thing that says, because finally your loss functions vary from model to model and use case. So you cannot say that use this metric to know exactly what the loss due to quantization is. So a debug tool could just say, this is like the ranking of sensitivity of different tensors in your model. So ideally you should not be quantizing this. That's sort of the first step. But in the longer run, you could say that given my loss metric, this is sort of the order. These are the choices. Maybe I will quantize just layer n because it's the least sensitive to this loss function. And the next layer I would quantize is layer k. And here is a tool that gives me like even better. That gives me a bunch of quantized models corresponding to different configurations of the model being quantized. And finally, as an end user, I just pick which of these n models is acceptable to me based on, finally, there's a trade-off, right? With quantization is always a trade-off between sort of the loss, additional loss you're getting versus the speed up that you get.
Cool. All right. Thank you so much.
Sure.
Follow up.